all to thank the organizers, Zhonghe and Yongnam, for organizing a conference on algebraic surfaces and moduli, which are my favorite subjects. And it's good to be here together with several friends. And so I decided to give a talk about some small recent results and posing also some question. By the way, you might wonder why I have always a jacket, but now you know, because there is like these microphones hidden in the pockets. So what is the general setup? So I want to pose some general question. I assume that S is a minimal surface of general type, and for simplicity over the complex numbers, as though many things will work equally well otherwise, and I have PG, which is the number of sections of the canonical sheaf, and Q, which is H1 of the same sheaf. And regular means Q equals 0. Now the question, so I will also denote by phi 1, this will be the mapping associated to the canonical system. From S, it is a rational map, and I will denote by sigma the image in the projective space of PG minus 1. And there is a definition that S is a canonical surface or a simple canonical surface and this means that phi 1 is birational. In this case, the canonical degree is smaller than the volume the canonical volume, but we have equality if and only if the canonical system is base point free. Now the condition that the map is birational onto its image, this implies so S canonical surface implies that PG is at least 4, and the classical theorem of Castelnuovo says that K squared is at least 3 PG minus 7. So there are certain inequalities. Now the first question question one is what are the maximal, so given PG, what are the maximal canonical degree and k squared and canonical volume for a canonical surface? So, for a simple canonical surface. Now, there is, of course, the inequality by Bogomolov, Miyaoka, and Yao says that k squared, so G is smaller than k squared, which is smaller than 9 chi of S, which is 9 pg plus 1 minus 9q, which is 9 times pg plus 1. So we see immediately from this formula that to get large canonical degree, it is convenient that q equals 0. Even if we have, and so especially we're interested for PG equal 4, 5, 6. We know that a priori, respectively, k squared is at least 5 and 45, respectively 8 by Castelnuovo, and then it is 54 and respectively k squared, we know that lies in these intervals between 5 and 45, respectively 8 and 54, respectively between 11 and 63. Okay, now we can also pose other questions. So I would like to pose several questions because after all these are important to pose questions and not only theorems. The question 2 is same question for the case not only where phi 1 is birational, where phi 1 is an embedding. Now, this question is interesting if PG at least 6. Since, for instance, if PG is 4 and phi 1 is an embedding, this is a smooth surface in P3, and by adjunction, well, the canonical system is the hyperplane system, so is the surface of D is equal 5. As D equal 5. And then there is a folklore theorem the folklore theorem says that if Pg equal 5 and phi 1 embeds, if and only if S in P4 is a complete intersection of type 4-2 or 3-3. In particular, D is 8 or 9. So this theorem, so I say folklore theorem, you can find the proof. I refer to an article which I will denote homological algebra and algebraic surfaces, and is contained in my long article on the AMS Summer Conference 95. So the main point of, the idea here is quite simple. The main point is that if a surface maps to P4, you have the Severi double point formula. By topology, it must have some singularities. And so if you unravel it out, you find that the degree is only 8 or 9, and then you treat this by hand. So if you have a surface in P4 that exists, we use Severi's double point. And now every surface can be embedded in P5, and so the question is really for starts from P5 on. Okay, so this is what I wanted to say. Now I want to put a question 3. And dicto means the same question. What are the degrees? Let me say it. Find D and K squared for S with Pg equal 4, such that sigma in P3 has ordinary singularities. So the ordinary singularities are the singularities of a general projection, which are analytically a double line or a triple point or a pinch point So this is the real picture. Over the reals it was rediscovered by Whitney. So, and one can ask also the same question for the same question for Pg equal 5 and sigma with what Severi called improper double points. Improper double points means analytically like two C2 intersecting transversally. Okay, so these are the general problems which are easy to state and a little bit less easy to solve. So let me right. Okay, so let me go to the second part, which is the state of the art for PG equal 4. And then there will be a third section which will be devoted to PG equals 6 and the interesting relations with homological algebra, which are also an important source of motivation. Whereas PG equals 4 is more really for people who like algebraic surfaces. Okay. So what is the state? So the number of people who work here is very huge. For instance, Kodaira, he constructed surfaces with K-square 7 and by some deformation argument. And the main point is that for K-squared between 5 and 10, Enrique's book, chapter 8, was devoted to sketching. So Enriquez and then Franchetta sketched the existence and then this was proven, existence of sigma with ordinary singularities, and this was proven by Ciliberto in 1981. So I have to say that this is sort of embarrassing that concerning question 3, this is all we know. On the other hand, if you look at the proof of Ciliberto, it involves some non-trivial arguments of about commutative algebra and contact. So the proof is not easy. Okay, then the next step. So and then I should say. So this was concerning question 3. I should say that concerning classification, so we are in the under the condition PG equals 4, K square 5, 6, 7, these are classified by Enriquez, Horikawa. Horikawa did clarify the case K square 6, and then Ingrid Bauer classified for K square 7. But even if these cases are completely classified, there are still some open questions concerning the moduli space. There are open questions remain questions whether irreducible components of moduli space are also connected components or not. So I would like first to give some general information. So I think there are some bounds for k² equals 6. Together with Ingrid and Roberto Pignatelli, we proved that the number of connected components is at most 2, but still there is some difficult things to decide. Now let me go to the question 5 was posed by Enriquez. So Enriquez expected that if S is canonical with PG equal 4, then k² would be at most 24. And the reason why he made this conjecture was because the expected number of moduli is, in general, is 10 chi minus 2 k². So in this case, PG 4 and Q equals 0, so this is 50 minus 2 k², and he was expecting this to be strictly positive. So k² should be strictly smaller than 25. Now, the answer, this question is completely answered, and the answer is no. So, first of all, Bourgnat proved that there exist canonical surfaces with k² between 11 and 16, and after this AMS conference, in the volume dedicated to Hirzebruch, I proved that there exists canonical surface with k² between 11 and 28, and D is equal to k², and the max is 28. And so, in the method, is the method of the following. We take Q is P1 times P1, and then we take Y is a singular bi-double cover. So, which means that Y divided the Galois group is Z2 squared, and the quotient is Q, and S is the minimal resolution. So this method, I have to say, was pioneered by Bourgnat, but somehow it needed some cleaner formulae in order to calculate the invariance and the canonical map. And I should say that Littke in his master thesis, he proved there exists a canonical surface with k² equal 31, but D equal only 12, I think. There is a reason why I have this. So in fact, he was disappointed that the canonical degree is much, much smaller than the canonical volume. And in fact, in the article, yeah, okay, so now here, this is the situation, and now there are later on with Ingrid, we showed there exists a canonical surface with PG equals 4, Q equals 0, K squared is 45. Now, this is exactly the maximum possible, but the canonical system has a fixed part, and so D is 19. This surface will appear probably also in some of the next lecture. This is again, Littke also was considering some other abelian coverings. It is a singular cover with G is Z mod 5 squared of P1 times P1 branched on, well, you take X, Y equal zero, 1, infinity plus the diagonal, and this amounts to taking, when you blow up these 3 points, you get a del pezzo of degree 5, and it's also of P2 branched on a complete quadrangle. A complete quadrangle, this means you take 4 points, and then you take the 6 lines joining these 4 points. Okay, so you see that first of all, finding with ordinary singularities seems not so easy.
Is there an interesting cover in characteristic 2 if you have 7 lines instead of 6? The Fano plane?
The Fano plane, yes, in characteristic 2, yes.
Yeah. Is there some interesting surface there with this Fano plane configuration? Seems even more exceptional.
Yeah, with this group. No, I didn't calculate, yes, but you have to see that it's a good question, of course, yeah. We can discuss it. I mean, it's if you just take an abelian group, then yeah, it's no. Now, so I have to apologize. I will mention about some new results. So I will have a new result which is on archive, and then I have two other results which I proved Saturday, which means that I didn't write the proof in full details. And so this will amount for the fact that I will write theorem with a question mark, which means since I make sometimes mistakes. I checked again yesterday, but anyhow, it's better to be, algebraic surfaces are very slippery. So, now I have a new example. So what is the philosophy is that we want high k squared. Now the maximal, see this the surface here is on the line k squared is 9 chi, so this is a Ball quotient. Now if you want high k squared, there is another line which is 8 chi, and are those which are uniformized by the bidisk or are covered by a product of curves. So the so-called surface is isogenous to a product. So in a sense, this is something when we have time, or maybe some younger people also will be asked to work this out in more detail. S isogenous to a product, S is C1 times C2 divided by G. And so here, G acts freely. And now where this Galois group was 2 generated in the previous case, here the first example which I considered is G equal Z mod 2 to the 4th. And now Ci goes to, I assume that this is of mixed, unmixed type, so Gx on C1 and on C2. I assume I want Q equals 0, so I assume that this is P1. Hence, there are no invariant differential forms, and this is branched on Ri points. And now there is some numerical formula, and we want G1 is 21, G2 is 5, R1 is, so 1 is branched in 9 points, and the second is branched in 5 points. And so what happens, now if you branch on 5 points, since the group is Z2 to the 4th, there is only one choice. For this other, there is some calculations, and there exist S as above, with k squared S equal 40, and such that S is a canonical surface, but unfortunately D is only 32 because there are 8 base points. So you see that, of course, this is one choice, and it's worthwhile to look at more examples. Although I have to say this is the easiest group, and with abelian groups you just write everything with characters, so it's quite easy. I will in the end explain what are the basic calculations in this case. Okay, so I should point out anyhow that this is at least is a record winner surface, not for the canonical volume, but for the canonical degree. So let me continue with this general that's okay. Information. So PG equals 6 and homological algebra. So this is somehow the main reason why I started again to look at these problems. And so this is related to some question which was posed some couple of years ago by 2 people working commutative algebra and geometry, the Kapuska. They asked whether if one is an embedding then the canonical degree should be at most 18, which was, of course, I said this cannot be because in theory it should go up to 63. Okay, so it's really, there is a lot of room. I mean, so let me explain you now what is the reason why there is some misunderstanding in the field. So from the point of view of homological algebra, what the key word is Pfaffian. So let me give the definition. A variety of dimension n minus 3 of codimension 3 in Pn is called bundle Pfaffian if there exists E, a vector bundle of rank of odd rank 2k plus 1 and alpha from I take the twist of the dual of E by a certain positive number, and I get this linear map from E dual minus T to E, such that alpha dual is minus alpha. So you see that alpha dual goes from E dual to ET, but twisting by minus T, you get the same map. Now, you have this vector bundle and you have this antisymmetric map. Now you know that if you have a matrix which is antisymmetric of odd order, the determinant is 0, but you can take the Pfaffian. And then X is defined.
Where is the bundle? Is it on the projective space?
Yes. Thank you. I think I wrote it here, and yeah. X is defined by the 2k Pfaffians of alpha. And we say that split Pfaffian this is the easy case, means that E is a direct sum of line bundles on Pn. So on projective space, so this is not so easy as taking complete intersections, but still it's something relatively free. So okay. In general, there is a resolution, a self-dual resolution, 0 goes to O minus T minus 2S. We take this map and we twist by S, then with alpha we go to E minus S, and this goes onto the ideal sheaf of X, which is the same to say that this goes onto OP and this goes onto OX. Now, this is given by alpha, this is given by the Pfaffians of alpha, and this is given by the Pfaffians of alpha, up to a sign, where I always make mistakes, but anyhow, this sequence is exact. Now, this implies that X is canonical, is how to say, it's not really canonical, subcanonical or whatever. OX is OX T plus 2S minus N minus 1. Now, I guess the best thing to do, I already spoke about what happens if in P1 times P1 you blow up these 3 points. You get a del pezzo of degree 5. Again, if you blow up these 4 points here, you get a del pezzo of degree 5. A del pezzo of degree 5 sits in P5. And it is the easiest example of a Pfaffian. So, example 3.2 is the case where we get 5 copies of O minus 3, 5 copies of O minus 2. Alpha is a matrix of linear forms. So 5 by 5, we take the fourth Pfaffian. We take now a 4 by 4 minor, principal minor. The determinant is of degree 4, but the Pfaffian is a square root of the determinant, so it's given by a polynomial of degree 2. So there are 5 principal minors, and the 5, and so this is given by Q1, Q5, and this goes to the ideal of X. So this is now generated by 5 quadrics, and the upshot is that X is a del pezzo of degree 5. And I've been having fun in the last month or whatever in finding out this X has some S5 symmetry, and there are very nice representations of S5 occurring. Everything is a representation, and you can identify something via the something which I'll explain on Thursday, the icosahedral symmetry. So this is the first example, and then okay, Walter proved the basic theorem So this was a conjecture of O'Connick, and Walter brilliantly adapted some previous theory by Horrocks and says that if X of codimension 3 in Pn is locally Gorenstein and somehow subcanonical or whatever, so omega is OP, then X is Pfaffian. Now, if n minus 3 is congruent to 0 mod 4 and P is even, need that chi of OX P half to be even. There is a technical condition, but you see in particular, if you take a surface in P5, this is not true. So for a surface in P5, it is always bundle Pfaffian as long as it is Gorenstein, locally Gorenstein, and subcanonical. Okay, so the next theorem, it's again a folklore theorem in the sense that I wrote it up and it was known, I mean, it's just an exercise. S is canonical and split Pfaffian if and only if k squared lies between 14 and 11. So now let's see why. I mean, I don't give you the numbers. I mean, there is some calculation. I already saw that if it's canonical, k squared should be at least 11. Why do we have the upper bound k squared equal 14? Now, the upper bound, this upper bound here, comes because the following considerations. If it's split Pfaffian, this implies that Q is 0 and S is projectively normal, because it's arithmetically Cohen-Macaulay. Now, if it's projectively normal, this implies that the surjection H0 of OP52 surjects onto H0 of 2kx, ks. But this has dimension equal 21. And this has dimension, chi plus k squared, which is 7 plus k squared. And so you see immediately that k squared should be smaller or equal to 21 minus 7, which is 14. So this range is rather small because there is a very strong condition that now, so what I did at that time, I was having fun with homological algebra, and I wanted to understand, actually with Casnati we extended these ideas of Walter in some other situation, and then I decided in the survey paper to work out the theorem of Walter. And so the next theorem which I proved, which is less folkloric, some examples were known to Schreier, but I proved that I classified the case k squared surfaces with Q equals 0 and k squared between 15 and 17. Now, this bundle here, E, is not any longer a direct sum of line bundles. So I have to tell you here E is equal. It's quite simple for k squared. Omega 1 P5 minus 2 plus 4 copies of O minus 3 for k squared equal 15. And you get for k squared equals 16, you take omega P minus 2, but you take now 2 copies plus O minus 3 for k squared equals 17. And now I don't tell you for k squared equals 17, this is complicated. So this theorem...
16.
Pardon?
16, previous case.
Yes, yes, thank you. Yeah, this is 16. So k squared 15 and 16, also you can obtain it as some sections of Fano threefolds, but this 17 is complicated. So now this is not hopeless. So what is the method? The method of Walter not only is an existence system theorem, but tells you also the method. So the main point is the Hartz-Rao module. So for simplicity, so the idea, so the recipe is that R of S is the canonical ring. So let's assume for simplicity Q equals 0, otherwise we have to add something. The canonical ring contains the coordinate ring of S. And the quotient M is a module over the ring of the polynomial ring. This is the so-called Hartz-Rao module. H1 star of Ix is the Hartz-Rao module. Now, this module is an Artinian module because it's a finite dimensional vector space. Now the recipe is that the recipe done by Horrocks, you take a Hilbert resolution, so a minimal graded free resolution of M, and then you truncate to the right. F1 is called the first syzygy module. And now, the method of Horrocks is that my E is stably equivalent to the Schiffification of F1. So E1 is just the Schiffification of F1, and E is just E1 plus a direct sum of line bundles. Okay? So there is this vector bundle, and to construct it, you have to understand this cohomology algebra. So until recently, so I mean, in a sense, there was a classification for degree up to 17. Recently, the Kapuskas brothers, I forgot what are the Christian names, there exists a canonical surface embedded. Canonical surface with k squared equal 18 and PG 6. So I'm still in the chapter 3, which are PG equals 6. So the method they construct is by the method by bilinkage. And the question which they raised in a previous version of this paper is D equal 18, the maximum. Now, of course, the answer should be no. Should have been no. In fact, I disprove this. But you see, it's something like when doing algebraic geometry and you take curves, varieties, there are two ways to describe them, through equations or as image of something. You take a curve, you can give the equation or give it parameterized. You take a plane curve with the maximal number of nodes. Try to construct it with the equation, it's a mess. But then you take a mapping of P1. So this is a rational curve. Now, life is not so easy for surfaces, as everybody in this room knows, but at least I could prove, and this is already on archive, the following theorem. Some surface which I'd already constructed in this article, I proved that is canonical. So I take S is by double cover of Q, which is P1 times P1. And the branch divisors has normal crossings. And D1, D2, and D3. And these are of bidegrees of type 2, 3, 2, 3, 4, 1. So I take something which is branched on these three divisors. The divisors are smooth. They intersect transversally in a certain number of points. And now I claim that S is simply connected, and phi 1 embeds if the 12 points where the first two curves intersect have distinct images by the second projections. The second projection onto P1. So if these 12 points have distinct images, then I can prove that now, and this property on an open set, which is different from the empty set. Let's see. So the idea, to prove that something is an embedding is not so easy, but in this case is that di is given by delta I equals 0. I have a polynomial bihomogeneous of respective degrees to 3. So now on S, we let yi to be the square root of delta. Since we take a double covering branched on this curve, this equation becomes a square.
So what is the relationship between this theorem and the theorems on canonical degree?
That's good. I was trying to run. And here, thank you very much. See, when the time is running, I get nervous. So here, PG equals 6, Q is 0, and K squared is 24. So thank you very much. This is the first counterexample to this question. Now, why here it is easy to do the calculation? Because there are square roots of these things, and then on Q I have coordinates U0, U1, and V0, V1. And now it turns out that the canonical map is given by Y1 U0, Y1 U1, Y2 U0, Y2 U1, and then Y3 V0, Y3 V1.
Sorry, just to understand. In question 6, you really mean d equal 18 or k square equal 18? Otherwise I don't understand. It's the same?
In this case, if it is an embedding, if it is an embedding, then it's base point free, and so k squared equal.
Sorry,
No, you must be tired. This is more than understandable. Okay, so the main point is that really there are the square roots, and then I can write everything explicitly. Now, more examples.
5 minutes.
Okay, thank you. So, there's another theorem with question mark that exists as isogenous to a product with k squared is 56 and ks is free, and this is phi 1 is birational but not an embedding. This would have been great, but it turns out that the mapping is birational, is a birational force, but it is not injective. The canonical degree is a record, but still we are looking for, now I would have liked to tell you something, but now I skip it. And now there are other candidates, and here you see, it's even more. If I did the calculations today ago, I put a question mark, but if I gave it to a student, then I cannot even put a question mark, so I say some candidates, and I hope that the answer is yes, but it's not finished. Other candidates S is a polarization, is a generic polarization of type 1, 2, 2 on an abelian threefold. In this case, Q is 3, PG is 6, and K squared is 24. So this is this should be, at least for generical choice. Excuse me?
A3 is an abelian variety.
Thank you, Miles. Thank you very much. This is an abelian variety of dimension 3 with a polarization of type 1, 2, 2. Yeah, thank you very much for the question. So, you see the self-intersection, so in this case, Ks is really OSS. And, I mean, so this is being, Cesarano is working on this. And then there is also some other interesting example. I take septics with 14 triple points in P3 exist, and there is still to be proven it's an embedding, but it has to be still, there is some Macaulay program, magma program, maybe Macaulay works better. It's not yet clear that it is injective. There is work of Weigel and people, and here PG is 6, Q is 0, and k squared is 21. And I've come to the end of my lecture saying, well, things are, I mean, most questions asked from wishful thinking are false in the case of surfaces. Still, I don't have enough candidates for going further. Probably, surface is isogynous to a product. Other might do a better job, but who knows? Thank you very much for the attention.